Right, so in this question, the basketball player clearly throws the ball towards the basket, okay? So he's projecting it from point P, which is 2.2 meters above the ground, right, with his arms outstretched. Now what you want to do is think of point P there as your origin, okay? That's the best way, I think. So where the ball is projected from becomes your origin. So I've set that up there in my diagram here, okay? So you can see then, here's the initial velocity, which is given in the question. Okay, so we're told this, projected at that speed, and there is my origin. So you can see, so my x-axis then and my y-axis here. And we know then that we've got this height above the ground here, and there's the basket. So in part A, it says, by considering the point Q with the position vector 3.5i plus xj, find the time taken for it to get to point Q. Well, of course, at point Q, all right, we want to find t, don't we? But we know the position vector is 3.5i plus xj. So it's quite interesting to note, isn't it, from the diagram itself, okay? And the one I've drawn here now, 3.5i, well, it's going to be above the basket, isn't it? Okay, it's going to be in line with the basket, rather. Okay, it could be above or below. We don't know. We don't know what the j value is here. Okay, but we know at Q, S is equal to this. That's this position. Okay, we also know the acceleration. So don't forget now, it's moving under gravity. So acceleration will be acting downwards. So minus 9.8 j. Okay, so if we then use S equals ut plus half at squared. Okay, so S is 3.5i plus xj. U, now of course we know u to be 7i plus 4.05j. Okay, that's given in the question, times t then. Okay, so the t we want is the time at Q, isn't it? So we'll call it, say, capital T. Okay, so t is the time at Q. Okay, plus then half, well, minus 9.8j for the acceleration, and then t squared there. So what I would do here is I would just simply tidy this up a bit here, okay, and you could see then we've got 7ti, if I multiply out there, plus 4.05tj minus 4.9t squared j there. Okay, and what I can do then is group the well, it's just one item, isn't it? So it's just that. The j term, there's two of these, so I could group the j's as so. Okay, and what you can do then, what's good about vectors is that the left hand side has got to be equal to the right hand side, so the I components have got to match. Okay, so in other words, what's in front of the I here, 70, has got to equal what's in front of the I here, which is 3.5. So then to get t, you just take the 7 over, okay, because the I is sort of matching up there, yeah? So the 70 has got to equal the 3.5, that's what I'm saying, in front of the i's, we've got to have them the same. So t will be 3.5 divided by 7, which is 0.5, okay, 0.5 seconds. You might have noticed that anyway, because the 3.5i is travelled across 3.5i, okay, when it's got an initial velocity of 7 horizontally. So basically, remember now that doesn't change the velocity horizontally, so it's always going to be 7. So if we can do 7 meters per second, well, 3.5 meters is like half of that, isn't it? So it's going to do it in half a second. And then in part 2 then, it does ask to show that x is 0.8. Okay, well, you can then match these up, can't you? You can say, well, the j's then, so we matched up the i's here. So with the j's, I've got, what have I got? Xj there equals to 4.05t minus 4.9t squared j there. Okay, so I can match them up. So in other words, I've got x will equal to 4.05. Now t I know is 0.5. So just quickly on my calculator, and indeed it comes out to be 0.8 meters. Okay, and what's interesting about that is, of course, is that when you look at the diagram, okay, so that distance there is 0.8 meters, isn't it? Because if you think about it, we've got 2.2 meters here. Okay, that's the height the ball starts with. So another 0.8 then will literally take us, so it will literally be above the hoop there, exactly where the hoop is there. Okay.